Welcome to the fourth part of our webinar series on linear motion technology. In this session, we'll focus on the machining of linear rails and shafts. We'll explain what matters most when it comes to custom machining solutions and what technical and logistical advantages they offer. We'll start by looking at standard machining operations like cutting and deburring, which are essential for processing linear components. Then we'll move on to special machining operations such as chamfering and butt machining of rails, as well as drilling on shafts. We'll also take a closer look at how mounting hole patterns, known as drilling patterns, are defined. As always, the webinar ends with a short preview of our next topic. Let's begin with the first machining method. Cutting is one of the very first and most important machining steps for linear rails and shafts. Manufacturers and distributors typically stock long raw lengths, ranging from 1 to 8 meters depending on the product. However, most customers require custom lengths for machine retrofits, special builds, or prototypes. That's why rails and shafts are cut to size on demand. Various cutting methods are used, primarily sawing and milling. Sawing, using cut-off wheels, band saws, or circular saws, enables fast and efficient processing. Milling, on the other hand, allows for greater precision and is ideal for producing clean-cut surfaces, chamfers, or grooves. After cutting, deburring is essential to ensure safety and functionality. Burrs are sharp material projections that can form during sawing or milling. They can damage seals, interfere with assembly, or impair performance. Sharp metal edges also pose a safety risk during handling. For rails and shafts, deburring is typically performed mechanically, using grinding wheels, brushes, or abrasive belts to smooth out edges. Shafts can be customized for a wide variety of applications, for example by drilling axial or radial holes. Depending on the complexity, this is done using conventional drill presses or CNC machining centers. Tools such as carbide drills, twist drills, or step drills are selected based on required precision, hole geometry, or depth. This allows keyways or mounting holes to be integrated directly. Additional processing such as polishing, anodizing for corrosion resistance, or CNC machining can also be performed, making even highly specialized drive and automation solutions possible. Key here is a clear specification of the required features, ideally supported by a technical drawing. Chamfering, the targeted beveling of rail edges, improves both safety and assembly efficiency. Beveled edges make it easier to insert the rail into its mounting and reduce the risk of injury during handling, especially during manual installation on site. Chamfering is typically done by milling. A rotating chamfering cutter is guided along the edge, removing material at a defined angle and depth. For example, a 45-degree bevel with 0.5 millimeter depth. Unlike deburring, chamfering is usually standardized, which is critical for consistent results in series production and for smooth integration with linear carriages. When rails need to be longer than standard stock lengths, butt machining is used. The ends of the rails are ground so precisely that no visible gap remains, with tolerances as tight as 0.02 millimeters. This is crucial to ensure that carriages run smoothly over the joint. After processing, the matching rail ends are laser marked, allowing installers to immediately see which pieces go together. This process allows multiple rails to be joined into one continuous precision guide, theoretically with no length limitation. In addition to technical precision, butt machining offers significant logistical benefits. The rails are easier to store and transport, come pre-configured, and are ready for installation. This reduces on-site labor, saves storage space, and simplifies handling, especially for large or heavy rails, where a single 6-meter section can weigh over 60 kilos. To ensure a smooth installation process, an accurately defined drilling pattern is essential. We'll take a closer look at this on the next slide. The drilling pattern defines where mounting holes are positioned along the rail, specifically the distances from each cut end to the center of the first and last holes. These measurements are key to ensuring accurate, secure installation. Depending on the rail type and manufacturer, these hole spacings are often standardized, with designations like G1, G2, or F. Drilling patterns become particularly important when rails are cut to length. This can result in either symmetric or asymmetric end distances, both of which must be clearly defined in advance. This is especially critical for butt machine rails, because if the rail's drilling pattern doesn't match the mounting surface, the installation won't work without rework. After machining, all components are thoroughly cleaned and treated with corrosion protection to ensure reliable performance. This makes them ready for immediate use. No extra steps required. For longer storage periods, we recommend regular condition checks to detect any early signs of corrosion and to take action as needed. In our next webinar, we'll explore track roller guidance systems and linear technology. We'll look at their structure, how they work, and where they are used. We hope you'll join us again. Thank you for your attention.